Hi class, this is Neil, and welcome to our first screencast as we kind of launch into remote learning. This is going to be new for all of us, so I really just ask for your patience, but also your questions and concerns. One advantage of posting videos is that you can always pause and rewind and rewatch things that you are struggling with. So let's go ahead and get started. This is going to be the first of 4 videos with this lesson. Let me kind of erase my work here. All right, so in the first video, I'm going to be reviewing the do now of this lesson. This lesson is on the growth and decay rates for various time units. And what we're really thinking about here is how do we adjust exponential growth and decay equations when the units don't match. So imagine we're given a rate that's in terms of years, and we want to rewrite it in terms of a rate that is aligned to months or weeks or days. And we're going to see how we can do this. But let's go ahead and look at the do now. So like a lot of exponential equations, this has to do with rabbits. Don't ask me why, but rabbits seem to have an affinity for exponential growth. So let's get started. Suppose a population of rabbits has been found in a small town. Scientists have collected data that shows there is a starting population of 43 rabbits. Scientist A predicts a 4% annual growth rate. How many rabbits would there be after 3 years? All right, so our growth rate here is 4%. So I'll write that as a decimal of 0.04. And our time unit is 3 years. All right, so this is just a pretty straightforward exponential growth model. So that equation again is given by A equals P, or what we start with, times 1 plus the rate as a decimal raised to the power of T, our time unit. So replacing what we know here, we know we start with 43 rabbits. We know that our growth rate should be written as 1.04. If I just add that 0.04 to 1, I get 1.04. And our time unit here is 3. So that's going to give me the total amount of rabbits after 3 years. All right, so I do need a calculator to evaluate this. One thing you could use is your phone. I really like the website Desmos.com, Desmos.com, because it has a lot of good graphing capabilities and sort of does what our calculators can do. So I'm going to go to the app for that. I'll just type in the equation we wrote. So that was 43 times 1.04. And this little a to the b button gets me into my exponent, and we're raising that to the power of 3. So that tells me after 3 years, I have 48 rabbits. All right, so let's look at part B then. So scientist B predicts a monthly growth rate. How many rabbits would there be after 3 years? All right, so in your eyes, what is the difference between part A and part B? All right, good. You should have said that in A, we're dealing with an annual growth rate, and B, we're given a monthly growth rate. The equation is going to be the same, though, the standard sort of exponential model. Okay, so the one thing I have to be careful about here, though, is our time is in 3 years and our growth rate is monthly. So to figure out how many months there are in 3 years, what would I need to do? Yeah, exactly. I would need to multiply 3 by 12 because there's 12 months in a year. So that gives me 36 months. All right, replacing what I know in this equation, I start with 43 rabbits. They're growing at 4% per month. And now our time unit is really after 3 years, we've gone through 36 months, so I write 36 there. Again, I'll need a calculator to evaluate that, so let me get into Desmos. Just change my decimal here to 36. And you're going to see that after 36 months or 3 years, we have 176 rabbits. All right, so the big takeaway here is really that the rate has to match, the time unit of the rate has to match whatever time unit we're using for the exponent. And we'll get into more detail about this later on. All right, let's look at question 2. A payday loan company makes loans between $100 and $1,000 available to customers. Every 14 days, customers are charged 30% interest with compounding. In 2013, Remy took out a $300 payday loan. Which expression can be used to calculate the amount she would owe in dollars after 1 year if she did not make payments? All right, so because this is a credit card and we're accumulating growth, we're going to need in our equation, in the rate part of the equation, to be adding that rate on. Okay, so because it's 30%, that's going to be 0.30. So inside the rate part of the equation, or inside the parentheses, we should see 1.30. So automatically, I can eliminate option 2 and option 1. So the real question here is what goes in the exponent. So 1 year has passed, and 1 year is the same as 365 days. So what we're really interested in here is how many times has the interest been added in? And it's being added in every 14 days. So I would need to divide that 365 by 14 in order to determine the number of times the interest is being added in. So option 3 is our best option for this question. All right, coming down to question 3, and then after this will be the end of this portion of the lesson and the end of this video. All right, so in question 3, we're asked to simplify each expression by evaluating what is inside the parentheses only. The first one's done as an example. So in that first question, what we did is just grabbed our calculator and plugged in 3 raised to the 1/8 power. And we get a little bit of a crazy decimal here, 1.14720.269. And I'm actually going to record as much of the decimal as I can. All right, so let's look then at question B, or part B of this question. So again, this is what I'm going to be inputting in my calculator. So let me go to Desmos. I'll X out what I have. So that was 1.6 raised to the power of, and just to be careful, I'll put it in parentheses, 1/8. Close the parentheses. All right, and so what we see there is it's 1.0605.1056118. Again, I'm going to record all of that information. All right, and I keep the exponent on the outside. All right, same for the second one, or part C. Same for part C. Again, I need my calculator to evaluate that, so let me go into Desmos. All right, so that's going to be 1.062, and I'm raising that to the power of 1/15. And again, I'm going to put in parentheses just to be careful. I don't have to. All right, so again, it's a little bit of a lengthy decimal, but I am going to record all of what I see here. All right, so let's go back. And that's going to be 1.00401,831,338. And that's raised to the power of 15x. All right, final one. So here we've got this 1 plus 0.0552 raised to the power of 1 over 365. And on the outside, we have that to the 365x power. All right, so again, I got to do this in my calculator. So I'm going to go to Desmos, and I can just input the entire expression if I'm using Desmos. Otherwise, you might need to simplify what's in the parentheses first. So I'm going to put 1 plus 0.0552, and that's raised to the power of 1 divided by 365. All right, and that's the decimal I have. So I'm going to record that. All right, great. So that's the do now. The next video, we're going to go over the first set of examples in this lesson, which have to do with finding rates for growth and decay for various units of time. And I'll see you then.